Welcome to Lyons Township High School AP Physics, and today we have an electrostatics example. You might want to spend a moment, pause the video, and copy this down, but it's a real simple diagram. We got three charges in a line, and there are 20 microcoulombs, 30 micro, and 40 microcoulombs, plus, plus, minus. I've labeled them A, B, and C, which is going to be useful. And then the distance from A to B is 50 centimeters, and from B to C it's 70 centimeters. And our goal is to figure out the net force acting on charge A. Okay, so if you need a moment, go ahead and copy that down. All right. So the first thing we're going to do is draw an FPD, just like in mechanics. All right. So here's charge A. Okay, and what we want to know is what do the other charges do to A. Okay. So what's B going to do to A? Well, B is a like charge, and we all know that like charges repel, aka that means push each other apart. So B is going to push A to the left. So I'm going to write that in as the force of B on A. I know it's left, okay, and I'll calculate a number in a minute. And then I got to look at what does C do to A? Okay, well, C is a negative charge, which is the opposite of the positive A. So C is going to pull A. We know that opposites attract, okay? So C is going to pull A, so we'll call that the force of C on A, okay? And we're going to find that number in a bit too. Now, what does B do to C? I don't care. I'm not asking about B or C. I'm asking what happens to A. We're done, okay, with our FBD. Now, later on, we'll talk about B and C, but right now we just care about what's happening to A. So we said, what does B do to A and what does C do to A? That's this. If you can do this and draw these directions correctly, you're 60–70% done with the problem already. Okay. Now, we're going to find the magnitudes of each of these forces, and we're going to use Coulomb's law to do it. So Coulomb's law says the force between two charges is equal to the electric constant K times Q1 times Q2 over R squared. So we'll start with the force of B on A. So I'll label this BA. This will be charge B. This will be charge A. And this is the distance from B to A. Okay? Okay, so the electric constant is 9 times 10 to the 9th. Q1 or QB is 30. And then a micro is 10 to the negative 6. So this is times 10 to the negative 6. QA is 20 times 10 to the negative 6. And then it's all over. How far is it from here to here? In meters. That's 0.5. And I've got to remember to square that. If you're not too comfortable with the calculator, I suggest you practice this and try this out. But if you plug all those numbers in, you should get 21.6. So double check that, make sure your calculator gives you that, make sure you can do the scientific notation reasonably and reasonably quickly. All right, and so that's 21.6 newtons, and that's to the left, so I'll put a little left arrow here, okay? And then we want to do the force of C on A. So that's going to be the same thing. It's going to be K, QB. This is going to be, this will be QC. I'll go and write this in. So K, QC, QA over the distance from C to A squared. Okay, so our electric constant is 9 times 10 to the 9th. QC is 40 times 10 to the negative 6. QA is 20 times 10 to the negative 6th. All over, how far is it from A to C? Well, we got to add up your 50 and 70. That's 120 centimeters or 1.2 meters. And I got to make sure I square that. Oh, note. Hey, note. What about the negative sign here, right? Hey, I don't put those in, okay? I already figured out that I used the negatives to determine the direction of the two forces. You are done with the negatives. The only negative you need in this problem is the exponents are negative. You better put that in a calculator, right? But like as far as putting negatives in for the actual signs of the charges, I don't ever do that. So you can if you want, but I don't suggest it, okay? So anyway, you can try this out in your calculator and make sure you get this right, but I got exactly 5 newtons. Now I'll write 5.0 there, and we know that points to the right. Okay, so what's our net force? Well, you've got a 21.6 to the left and you got a 5 to the right. They're going opposite directions. You're going to subtract them. You get 16.6 newtons. That's the net force acting on A. And it's 16.6 newtons. And who wins? Well, the left force is bigger than the right force, so this is to the left, or you can write left down, or you could, I guess you could write west if this was a north, south, east, west kind of a problem. So that's the net force acting on A, okay? Now, you might encounter problems where they ask you to then go and find the net force on B and the net force on C. You would do the same process, okay? So you would look at B. Now, here's the cool part. If you've done A already, you've done a lot of the work toward B. So let's say they asked you to find the net force acting on B. Well, what does A do to B? Well, it pushes it, so I'll put a little arrow there. That's the force of A on B. And you know what? We already know that number. It's 21.6, okay? You're going to be multiplying these same two numbers, opposite order. It'll be 20 times 30, but other than that, it's the same thing. So you know that number already. You don't got to rework that. What does C do to B? Well, C is an opposite charge, so he's going to pull. So this is the force of C on B. Now that number we didn't calculate before. So you would have to calculate that, but you would just do K times 30e negative 6 times 40e negative 6 divided by how far apart they are, which is 0.7 squared. You'd get a number. And they're both to the right. So in this case, you'd add up those two numbers, and that would be your net force. And then for C, okay, well, you look at what each of the other guys does to C. So what does A do to C? Well, A is an opposite charge of C. That's a plus and a minus. So A is going to pull on C. So this is the force of A on C. And by the way, you already know that number. It's the same as the force of C on A. It's equal and opposite. Oh, by the way, that's a little review. Newton's third law. If A pulls on C, or if C pulled on A with a force of 5 newtons to the right, A's got to pull on C with a force of 5 newtons to the left. Newton's third law still holds true even with electric circuits or electrostatics, electric charges moving around. What's B going to do to C? B is going to pull on it as well because these guys are opposite. This is the force of B on C. And hey, you would have already had that number by now because these two are equal and opposite. So you would already have those two numbers, and they both point left, so you would just add them up and get a net result. So that's how you figure out the net force acting on charges when the charges are lined up in a line. And again, I can't stress strongly enough, draw the FBD. Even if it's as simple as this, draw the FBD. So I hope that example was helpful, and thank you very much.